We want to talk about solutions, and we want to show that what is a solution to a differential equation. So I've got one very brief example. I've got y double prime minus 3y prime minus 4y equal to 0 is my differential equation. Y equal to c1 e to the 4x plus c2 e to the negative x is a family of solutions to the second order, so we know it's the general solution because this is second order, and I have two linearly independent solutions here. So this is the general solution to this differential equation. But now I want to find out the particular solution that satisfies these two initial conditions, y of 0 equals to 1 and y prime of 0 equal to 2. So what I want to do is take this, plug it into this, and solve for C1 and C2. So let's come down here and take the first derivative. So that would be 4 C1 e to the 4x minus C2 e to the negative x. Now notice I did not incorporate the 4 into the C1 because my whole purpose is to solve for C1 and C2. So don't make new arbitrary constants here. Now, since I have a second derivative, let's take the second derivative. So that would be 16 C1 e to the 4x plus C2 e to the negative x. So what I want to do with these is I want to plug them in to this differential equation. So this would be 16 C1 e to the 4x plus C2 e to the negative x. That's the y double prime right there. Minus 3, so this would be minus 12 C1 e to the 4x. Minus 3 times a negative becomes a plus 3 C2 e to the minus x. So that takes care of that guy. And then minus 4 times that. So that'd be minus 4 C1 e to the 4x minus 4 C2 e to the negative x. And all that's supposed to be equal to 0. So that took care of this last part. So I plugged it all in. Now we get apples with apples, oranges with oranges, kumquats with kumquats. So let's get all our e to the 4x's together. So this one, and this one. So I have 16 minus 12 minus 4. So what do I notice? Well, they all disappear. 0. Plug in these. What do you notice? They all disappear. So in trying to solve for C1 and C2, I see I didn't, but I did do this. I proved that this is solution to this differential equation. So I proved it's a solution to the differential equation. Now I'm back to square one again. How do I solve for C1 and C2? Well, let's just use this now and this in here to solve. So y of 0 equals 1, but it also equals C1 e to the 4 times 0 plus C2 e to the negative 0. So that, of course, is C1 plus C2 since e to the 0 is 1. Now, let's take the derivative. Well, I've already done that. So y prime of 0 equals 2. So I'm going to use this form. So this would be 4c1. Again, I know e to the 0 is 1 minus c2. So I have two equations, two unknowns. I don't care how you solve it. Two equations, two unknowns. You could use substitution, you could use elimination, you could use matrices, however you want to do it. But I think I will just take these two, and let me rewrite this with a 1 there, bring down that 1. So let's just add these right here. Why am I using that method? Because I noticed the C2's cancel out. So you get a 0 there. Negative C2 plus C2 is 0. 4C1 plus C1 is 5C1 equal to 3. So what do I end up with? I end up with C1 equals 3/5. So once I have that, I'm going to use this. 1 equals 3/5 plus C2. So C2 is equal to 2/5. Because 2/5 plus 3/5 is 5/5, which is 1. So what is my solution? The particular solution to this IVP, this initial value problem, will be y equal to 3/5 e to the 4x, C2 is 2/5, e to the negative x. So in doing this problem, I did two things. I showed you that it was a solution. This general, which is the general solution, is a solution to this differential equation. Didn't help me with finding the arbitrary constants, but it did prove that. To find the arbitrary constants, I just plugged it into the initial values right here and solve for C1 and C2. So here is my particular solution, and you could even write a y sub p there to make sure you show that it's a particular solution.